Hello friends, welcome to Geeks for Geeks. In this video, we are given a problem that is to find the sum of bit differences among all the pairs. The problem says that given an array of integers and we are required to find the sum of bit differences in all the pairs that can be formed from the given array. Now, bit differences, the word seems confusing. Here, bit difference of a particular pair, say x, y, is the count of number of bits that are different, or we can say complementary in x and y. For example, take arbitrary input as x equal to 3 and y equal to 6. Now, the bits that are complementary are highlighted here. Since we find complementary bits at two different positions, hence we say that bit difference of x and y is equals to 2. Now, our task is to count the sum of bit difference of every possible pair from the given array of integers. As an example, now take the input array consisting of 1, 3 and 6. There are in all 9 possible pairs shown here along with the count of their respective bit differences. For example, bit difference value of 1 and 3 is equals to 1 and bit difference of 1 and 6 is equals to 3. Now we take the sum of all these bit differences and return the sum as an answer which is equal to 12 in this case. Let's now carry on with the simple solution to this problem and then look for the better alternative. One of the simple approaches where we compute the bit difference value for the each possible pair one by one and then update the global sum variable with the sum of calculated bit difference value for the each pair. Here we would pair every element with all other elements in the array, and for the array containing n integers we would have n square possible pairs. As you might have seen in our previous example for 3 elements 1, 3 and 6, overall we had 9 possible pairs. Hence, this would take the time complexity of the order of n square. Also, in this case our space remains constant throughout, hence that would give us the space complexity of big O of 1. Now, apart from this, we have an efficient approach also, which would solve the given problem in the time complexity of the order of n. Let's go for that. An efficient approach is based on the fact that ultimately the problem is asking to count all the 0, 1 pairs at all possible bit positions. This approach assumes that each integer in the given array is a fixed number of bits, for example, say 32 bits. Now, what we do is we instead of going for every possible pair, we traverse each bit position, and for any arbitrary bit position I, we count the number of integers having the ith bit as set. Now, if the variable count stores the number of integers having the ith bit as set, then number of integers having ith bit as unset would be n minus count, and their product multiplied by 2 would give us all combinations of the all possible complementary bit pairs at the ith position. We compute this product for every bit in the 32-bit integer and add it to the global sum variable. At last, we return this sum variable as an answer. To make this more clear, let's take the same example again. Here, the binary representation of 1, 3 and 6 are shown and fixed bit length is assumed to be 3. Initially, sum variable is set to 0. Now, we first check the least significant bit and look for the integers having LSB as set. Here we find two such integers 1 and 3, so the calculated product is equals to 2, that is the number of integers having LSB as set, into 1, that is the number of integers having LSB as unset, into 2, which is equal to 4, and adding that to the sum variable it becomes equal to 4. Now we go on for the second bit and we again find two integers 3 and 6 having this bit position as set. So again the product is equals to 4 and adding this to the sum variable would give us the sum variable equal to 8. At last, we would do the same for the most significant bit and we find only one integer, that is 6, having this bit position as set. So the product again becomes equal to 4 and this time the sum variable becomes equal to 12. Hence, what we get is the sum variable equal to 12 as an answer, which is same as that being shown earlier. Now let's see the implementation for the given approach. Here we have a function named SumBitDifferences which takes the array of integers along with its size n as the arguments. Now we first take the answer variable and initialize that with 0. Next we run a for loop which iterates for each bit position of the 32-bit integers. Now inside for loop we take another integer named count which stores the number of integers having the ith bit as set. We calculate those integers by running another for loop with the value of j from 0 to n. Each time we check for the set bit at the ith position by taking the bitwise AND operation of the integer with the one left shift I. And if we find the bit as set, then we increment the counter count. Further, in the external for loop, we calculate the product of count into n minus count multiplied by 2 to get all possible 0 1 pairs at the ith bit position and finally add it to the answer variable. This answer variable at last would give us the sum of all the bit differences among all the pairs. The complexity analysis of this approach is as follows. Since the length of external for loop is kept fixed, hence we would consider only the inner for loop for the complexity, and since it iterates over all the integers in the given array and array has n integers, the algorithm takes order of n in time. And since our space requirements remains constant throughout, the space complexity remains big O of 1. I hope you have understood the two ways in which we can find the sum of bit differences among all pairs. Thanks for watching. Please leave us your comments.